Welcome to Net Zero Carbon Architecture. I am Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. While our earlier sessions on net zero energy design focused on buildings' operational energy only, net zero carbon design expands beyond operational energy. It addresses the carbon impacts during the building's entire life cycle. By the end of this session, you will learn how buildings can embody these principles to reduce and offset their carbon footprint. Now let's discuss net zero carbon design. Similar to the net zero energy, this framework also emphasizes reduce in both embodied and operational carbon, and then it applies regenerate using nature-based solutions to offset the resulting carbon emissions. On the reduce side, we need to minimize embodied and operational carbon as much as possible using bioclimatic design and energy-efficient building service systems. We also need to choose low-impact, low-carbon materials. The other side, regenerate, relies on renewable power production to operate the building. Finally, it incorporates nature-based carbon uptake to remove carbon emissions from material production, construction activities, and building operations, etc. Nature-based solutions are applied at the building and site levels. Let's compare the design approaches for zero energy versus zero carbon goals. At first glance, they may look similar, but there are important differences. Both use reduce and regenerate framework. While net zero energy focuses on balancing operational energy use and renewable power production, the net zero carbon is more difficult to achieve. It requires additional strategies like using heavy timber and CLT and incorporating real-time carbon sinks such as green roofs, green facades, and constructed wetlands. This comprehensive approach minimizes carbon, reduces waste, and restores a healthy and resourceful built environment. Additional videos are available for each strategy. Please refer to them for more information. This slide explains another reason why we need to push further to implement carbon-neutral practice. We looked at IEA's roadmap to meet carbon neutrality in the building, manufacturing, transportation, and energy sectors. In that roadmap, by 2030, all new buildings must be zero carbon ready, and more than 85% of both new and existing buildings must achieve zero carbon status. This chart projects US building floor area. The building sector is projected to build additional 170 billion square foot of new construction into 320 billion square foot of building stock constructed prior to 2022. This will result in the construction of millions of new residential, commercial, and educational facilities. If these are built with conventional practices, the operational and embodied carbon emissions would be enormous. These projections underscore the fact that even though new construction happens, most buildings in 2050 will be retrofitted from existing building stock. Designing and retrofitting obsolete buildings with low carbon principles presents a critical opportunity for emission reductions. Every new square foot needs to be designed with aggressive energy reduction and decarbon strategies because the cumulative impact is huge. Now we delve into bioclimatic design, one of the reduce strategies. This slide lists fundamental design tactics that leverage the local climate to minimize energy use. Key bioclimatic elements include building orientation, window areas and orientation, nature ventilation, natural cooling, daylighting, passive heating, and so on. Positioning and shaping the building to optimize sun and wind exposure. For instance, placing a building's longer facade along the east-west reduces overheating due to smaller east and west glazing and larger north and south exposure for controlled daylight. Natural ventilation reduces mechanical load while supplying clean air to spaces. Daylighting reduces artificial lighting demand while providing connections to outdoor views. Passive heating utilizes sunlight during colder months and reduces heating load. Additional videos on bioclimatic design are available. All buildings, systems, and components carry embodied carbon resulting from carbon emission associated with manufacturing, transportation, and construction activities. Choosing low carbon materials connects to the reduce framework The chart on the right compares the embodied carbon and embodied energy of structural materials for a unit weight. Embodied carbon refers to the total greenhouse gas emissions associated with the manufacturing, transportation, and assembly of materials, expressed as kilograms of CO2 equivalent per kilogram of material. Embodied energy is the total amount of energy consumed during the manufacturing, transportation, and assembly of materials, expressed as megajoules per kilogram of material. Glulam materials have negative embodied carbon of minus 0.76 kg CO2 per kilogram because they store carbon during their life cycle. Steel, on the other hand, emits 2.7 kg CO2 per kilogram. Concrete has a moderate impact with 0.15 kg CO2 per kilogram. Now let's look at embodied energy in megajoule per kilogram. Glulam materials have an embodied energy of 8.9 megajoule per kilogram due to the manufacturing process involved in producing engineered wood. Steel has 42 megajoule per kilogram of embodied energy due to an energy-intensive manufacturing process, making it far more carbon-intensive. Using steel with a high recycling content can reduce its carbon footprint. Concrete materials are around 1.09 megajoule per kilogram. Just as selecting structural materials with low embodied carbon is essential, choosing low-impact materials for facades is equally important. This chart compares the embodied carbon and embodied energy of facade materials such as bamboo, rammed earth, brick, and aluminum. Renewable biomaterials have significantly lower environmental impacts compared to metal and plastic. Having a high recycled content is essential to reduce the carbon footprint. Slides 8 and 9 showed the embodied carbon and embodied energy for traditional building materials. These reference data sources are from the IPCC 6th Assessment Report, which we used in the previous slides. Choosing materials with low embodied energy and carbon constitutes an action strategy critical for carbon-neutral construction. Addressing these impacts assists us in making more informed and sustainable material and technology selection. This slide highlights various material innovations that significantly reduce embodied carbon. Additional videos on circular economy and sustainable materials are available. For example, bamboo and CLT, cross-laminated timber boards are renewable, low-carbon alternatives to traditional flooring and structural materials. Mycelium and Bioconcrete materials are breakthrough materials that not only reduce carbon but also regenerate building materials. Recycled materials such as recycled rubber roofing and denim insulation are creative examples of turning waste into functional building materials. The use of low-impact materials aligns with the REDUCE framework. Achieving net zero carbon isn't just about new technology. It also requires rethinking how we use resources in a regenerative loop. Low-carbon practices make it possible to construct buildings that are not only lower in emissions, but some that store carbon in their fabric. Now let's shift to efficient systems and renewable integration as the next pieces of the puzzle. This slide shifts focus on the technological side of reducing energy consumption. The use of energy-efficient MEP systems and LED lighting achieves low energy consumption while providing comfortable environments for users. Building Management System, BMS, is a computerized central system that monitors and optimizes entire building operations. This high-performance service system is integral to the REDUCE framework, complementing bioclimatic design to further minimize energy demand and enhance occupants' health and well-being. Sustainable MEP integration video is available. The final strategy of net zero energy design is the integration of renewable energy systems. The ability to generate clean energy effectively allows the building to offset the remaining demand after bioclimatic design and energy-efficient systems integration. Examples shown here demonstrate a wide range of solar applications at the infrastructure level, such as photovoltaics, solar desalination, solar farm, and solar canal. In urban settings, examples include solar-powered street lamp, solar benches, solar parking decks, and solar acoustic barriers. In building integrations, examples include facade applications such as Blauhaus, Novartis Pavilion, and FKI, and roof applications such as Apple headquarters. These examples convey that integration of renewable energy strategies is versatile. By designing from the start with renewables in mind, whether it's BIPV on a curtain wall or a solar panel on a parking structure adjacent to buildings, we ensure that clean energy generation is harmoniously built into the project, paving the way for net zero energy operation. BIPV design and engineering as well as solar facade videos are available. Finally, buildings contribute to both embodied and operational carbon emissions, making real-time carbon sequestration essential for achieving net zero or even carbon negative buildings. This slide features iconic examples of integrating nature into buildings. Park Royal Pickering in Singapore is a hotel that incorporates lush greenery on the balconies of hotel rooms. It provides a biophilic experience for guests while enhancing carbon capture. Wisma Dharmala Tower in Jakarta, Indonesia by Paul Rudolph is an early example from the 1980s of bioclimatic skyscraper design. It includes exterior garden terraces at multiple levels, which help shade the facade and cool the building naturally in the tropical climate. Vertical Forest in Milan is a high-rise covered with trees and shrubs that act as a living carbon sink. Le Nouvel Tower in Kuala Lumpur integrates vertical gardens along the facades for various flora for carbon sequestration. Haus E in Zurich by MSA is a sustainable house project in Switzerland. It is noted for energy self-sufficiency and a green roof living wall blend with nature. Landscape Rift in Denver, USA is an avant-garde design concept where the buildings mimic a slice of earth, with greenery and landscape integrated into the structure. The idea is literally a building merging with the landscape, inviting nature in as part of the architecture. Nature-based carbon sink is a critical step to achieve net zero carbon buildings. They integrate greenery and living systems as part of their design, modulating microclimates, sequestering carbon, and preserving biodiversity. Additional videos on resilience and biofacades are available. We now look at nature-based carbon sink strategies explicitly. The California Academy of Sciences in this slide illustrates how green roofs contribute to high-performance building, carbon capture and aesthetic values, and seamless blending with landscapes and urban surroundings. Nature integration can be done at the building, site, and community levels. This museum famously features a large living roof, 2.5 acres of native plants blanketing its undulating roof surface. That living roof not only insulates the building and provides habitat, but its plants absorb CO2 from the atmosphere as they grow. Let's look at a project located in hot and humid climate, Perez Art Museum in Miami by Herzog and de Meuron, completed in 2013. The big roof canopy creates an interstitial space with hanging vegetation that resembles verdant curtains. The site is planted with drought-tolerant grasses and plants. Suspended vegetation and landscapes enhance the comfort of the urban microclimate and public spaces, functions as carbon sinks, and improves air quality. Another innovative nature-based carbon sink integrates microalgae living components into building systems. This slide shows a microalgae window system installed at UNC Charlotte. Biochromic changes color in response to biological activity. Building surfaces could be treated as living functional systems, almost like artificial leaves, scrubbing CO2 from the air. The window cleans indoor air and links environmental performance with an aesthetic performance display. It regulates solar penetration, enhancing both environmental and occupant health. Regenerative architecture can actively become part of the carbon cycle in a positive way. Whether through planted roofs and facades or through new bio-integrated technologies, buildings can go beyond just reducing emissions. They can capture carbon and produce oxygen. This slide illustrates some data to quantify nature's carbon sequestration power. For example, the wetlands sequestration rate has the highest rate at 23 kilograms CO2 per square foot per year, meaning even small areas can have a significant sequestration impact. In other words, a piece of healthy wetland the size of a floor tile has the capacity to take in dozens of kilograms of CO2 every year, a tremendous rate. Refer to the additional note in the pink circle for the conversion rate. Incorporating constructed wetlands into site designs significantly contributes to carbon sequestration while creating functional and beautiful landscapes for public access. Like the previous comparison, this graph compares the carbon sequestration capacity of different individual plant types, measured in kilograms of CO2 per square foot annually. Vineyards have the smallest biomass and sequester approximately 0.4 kilograms CO2 per square foot per year, the lowest in this graph. By comparison, microalgae are the most effective carbon sink, capturing up to 4.5 kg CO2 per square foot per year. The reason microalgae have the highest sequestration rate is they consist of photosynthetic cells with high photosynthetic efficiency, allowing them to absorb more CO2 in a shorter period. Now we bring it all together with a practical example. This considers typical buildings' emissions versus what's needed to offset them with natural systems. Let's use a 50,000 square foot office building with an annual operational carbon emission of about 8.7 kilograms CO2 per square foot. Multiplying out 8.7 kilograms CO2 per square foot x 50,000 square foot gives 435,000 kilograms CO2 as the total emissions for the building's operations. How much wetland area of carbon sink would we need to neutralize 435,000 kilograms of CO2 annually? Using the earlier number for a wetland sequestration rate, 23 kilograms CO2 per square foot, this would require approximately 19,000 square foot of wetland to offset those emissions. That's roughly a square of 137 feet by 137 feet, a significant size. In contrast, if we tried to offset the emissions with algae facades alone, using the high rate approximately 5 kilograms CO2 per square foot from the last slide, we'd need about 78,000 square of facade area. That equates to a facade approximately 280 feet by 280 feet, larger than the building's footprint and impractical to cover fully with algae panels. A combination of wetland on site, an algae facade, and green roof together to reach the goal, since relying on the facade alone is impractical. Offsetting all emissions of a sizable building is non-trivial. It drives home that we must drastically reduce emissions through efficiency and design lowering that 8.7 kgf T2 figure while expanding renewable generation and carbon sinks. In a design studio or practical context, one might take these numbers and plan a solution. Maybe reduce the building's consumption so emissions drop to 4 kilograms per square foot, then a smaller wetland or forest patch plus some algae panels could feasibly balance it out. Develop a site and building 3D section based on your carbon sink calculations. This is part of a student project, encouraging designers to physically integrate these carbon sink areas into their architectural proposal. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. Together, we can advance towards a sustainable and net zero future.